Okay, so continue that further. This is the other picture from the same experiment we saw in the last podcast with the heating pad at the bottom, potassium permanganate to make it visible, and so on and so forth. And you can clearly see the overshoot and the creation of the inversion. So this is the convection layer, which is becoming unstable and sending buoyant parcels up into the stratified stable part of the water column, and you can clearly see these inversions being visible when the convection layer overshoots into the stable layer. So that's a good example of how gravity waves get set up, right? So the other thing is to go back to the energy transport. Convection is obviously moving energy from the surface to the upper altitudes, which then is going to be taken poleward by the Hadley cell and so on. So what is the law of vertical heat transport? Convection generated fluctuating vertical transport. So you have to average it over a horizontal plane to compute the net transport. So these motions are always kind of, they're not just vertical motion and downward motion like the nice cells we saw. That happens when the motions are very slow and not very turbulent and mixing and so on, whereas in the real world we'll see that these motions can achieve tens of meters per second depending on how strong the convection is, and then as they go up they also tend to entrain air around them, and when heavy rain comes down, for example, you feel some cold air coming because that water also brings down colder air from aloft down with it. You will experience this a lot in a monsoon region, for example. Okay, so how do we do that? The heat transport denoted here by H is we are always doing per unit mass, so take some parcel as a unit volume. Rho times the heat capacity at constant pressure times W. What is W? It's basically the vertical motion of the parcel. Convection means basically vertical motion and the compensating downward motion, right? So temperature is the parcel carrying with it. As we said, we called it a parcel because it moves fast enough that it doesn't diffuse or mix heat with the environment, so we can almost consider it adiabatic. Adiabatic means it's not exchanging heat with the environment. So the parcel is moving fast enough through the environment that it's not mixing up heat, losing or gaining heat. So this T is of the parcel. Okay, what happens? Obviously, when you have a compressible fluid like air instead of the water we are looking at here, air rises, it expands, and even if it's a parcel and adiabatic, you can have condensation of the water vapor within. So things are going to get complicated. Nonetheless, if you look at a horizontal plane, then you can see what is the net vertical transport. Net because you might have upward, downward motion, so you have to look at fluctuating transports, but what is going across the plane on average. So average horizontally, it turns out to be approximately 1/2 of some reference density, Cp times Wc, which is the convective motion, times delta T, because remember we are always moving in an environment which has a temperature profile, so it is the change in temperature of the parcel that's going to determine how much net heat transport happened. Obviously we are doing this in a very simple hand wavy kind of way because we are not deriving the equations here. We'll look at the large scale transports a little bit later on in terms of what the Hadley cell carries and what the ocean meridional overturning carries and so on, but here it's done in a simple way. So Going back to our potential energy, we had PE final minus PE initial, and we had written it in terms of minus G d rho dz of the environment density profile times delta Z. And if you assume that the delta PE, because of the buoyancy mixing and the parcel movement, we have converted the potential energy into kinetic energy, and if we assume isotropy and that kinetic energy in all directions is going to be increased the same way, then you need a factor of 3 xyz. So you have the kinetic energy 1/2 rho wc squared. Remember, half mv squared is always the kinetic energy, times 3. Okay, that has to be equal to the change in the potential energy. Again, very simple, almost like an estimation of scales at which these changes happen. Okay, so you can write that as minus G rho 2 minus rho 1. So we're just replacing delta PE with this expression up here. Okay, so using our temperature relation of density, we can then estimate Wc squared in terms of thermal expansion, gravitational constant, change in the height involved in the convection, and change in the temperature involved in the convection. Why do we want to do this? Because we said hydrostatic balance where vertical motions are very small. So what are actually the vertical motions involved? So to estimate the rho Cp, the heat transport and the vertical motions, you can take typical scales at which these things happens. So heat transport in the experiment that was done in the tank that we looked at, it's about 4,000 watts per meter squared. We know that because we are putting in the heat. We know the delta Z over which the convection is happening in the tank, and we know the change in temperature that is being induced by the convection, which gives us, plugging into this relation, a vertical motion of half a centimeter per second, which may seem like small, but in a small tank like that, that's a pretty vigorous vertical motion, which can be measured by using some techniques because of the visibility of the potassium permanganate. So plugging that into the heat transport equation, you get the scaling dependence on temperature and height and so on. Again, just go through these arguments to see that in the real world we are moving parcels, we are changing buoyancy, we are creating potential energy changes which are converted into kinetic energy, and the kinetic energy is all about moving heat because it's all part of the energy transport. Okay, that's the main point you want to learn out of these. These experiment based scaling are obviously very useful. You should pay attention to them because we'll come back to them also in the real world to see what are the amounts of heat moved, what are the vertical motions involved. The way to think about hydrostatic balance is these motions are very fast, and the environment quickly adjusts the large scale to make the large scale still come back to hydrostatic balance. So the scale of the convection, etc., tend to be very small and very vigorous compared to the large scale motions. And the large scale motion keeps on going back to the temperature profile we saw and the hydrostatic balance. Okay, so you have to carry these things in your head in terms of reconciling seemingly different things we are saying, but this is the matter of scales.